It feels so normal, formal. So hello everyone. I'm doing a brief introduction to Anna Childs. She was a graduate student when I first met her at the UNLV, and I believe her bachelor was in math, but then now into astrophysics. And what impressed me a lot is that she was very productive, especially once she graduated from UNLV. And she moved to Northwestern University for a 3-year fellowship. And then she's crunching out papers by papers, including several with me. So today, I think so now she is working with me at Alabama, but remotely, still based in California. So today, I think she will present several of our work together. So Anna, is yours.
Okay. Thank you, Chao Chen, and thank you everyone for being here to listen um, to my talk about the work I have done, most of it with Chao Chen, starting at UNLV when I was a graduate student. So this is about 4 to 5 years of work, focused mainly on the formation of the TRAPPIST-1 system. Okay, so let's get right to it. So we were interested in modeling the TRAPPIST-1 system, which is, as most of you probably know, a very famous exoplanet system. And so it's been extensively studied, but we wanted to do something new, and that was to place constraints on the bulk composition of these planets throughout the formation process to see if we could predict any observables that James Webb might be able to see. And so, to model the formation of these planets, we took a stratified perspective towards this. And so, it started with adopting first a disk evolution model. Once we had a disk evolution model, then we also implemented a pebble accretion model. We included the effects of fragmentation. And then, with all of these aspects combined, we were able to model the assembly of compact systems. We then later extended these simulations without the stabilizing effects of gas to probe what type of dynamical instabilities happen in these compact systems. And then lastly, we compared these results to the observations. So a brief overview, if you're not familiar with the TRAPPIST-1 system, it is a very compact system. 7 roughly Earth-sized planets are found between 0.01 and zero point 0.1 AU from a very small M-dwarf star. TRAPPIST-1 has a mass of only 0.09 solar mass, so it makes it a very cool and small M-dwarf star, which makes this system even more special because of the high multiplicity and compactness. Um, there have been lots of studies that have looked at what leads to the stability of this system. And it's been demonstrated that it's the 2-body and 3-body mean motion resonances throughout the entire planetary system, as well as the 3-body angular resonances throughout the system that have contributed to the long-term stability. And contrary to how we think the terrestrial planets of the solar system formed, it's thought that the TRAPPIST-1 planets form primarily through pebble accretion, which leads to this compact structure. So it was Chris Hormel in 2017 who first put forward a very specific formation channel for the TRAPPIST system. And it basically states that you get your initial planetesimal population that forms just exterior to the ice line, which would be this black vertical line in this little schematic. So while the gas and dust disk is still present, these planetesimals start to experience gas drag. So they start to migrate inwards through type 1 migration. And throughout that process, they accrete pebbles. They undergo pebble accretion, which can very rapidly grow the planetary masses. And so this happens more or less subsequently, one planet at a time. The first planet, it forms, it migrates and it forms as it migrates inwards and continues to accrete pebbles, but it stalls at the inner edge of the disk cavity. The second planet then starts to undergo type 1 migration. It's moving inwards, but then it stops behind the first planet as it gets trapped in a mean motion resonance location. And this continues to happen until you get this long chain of planets that are locked in mean motion resonances. So we wanted to model that formation channel, but again, we wanted to do something new, and that was to see if we could constrain the bulk composition of the planets throughout this whole formation process. So to do this, we had to develop new numerical tools, and we had to combine these new tools with existing tools to get our final bulk compositions. So the first thing that we had to develop was a rebound X module that models mass growth through pebble accretion in an evolving gas disk, and also models gas drag forces on the solid bodies in the n-body simulations. We coupled this with composition results from a disk condensation code, which we use to initialize the starting compositions of the bodies in our n-body simulations. And then as a post-processing step, we track how the bulk compositions of the bodies change over time as they merge with one another and as they accrete pebbles from various regions in the disk. We then took those final bulk compositions and we fed them into an interior structure code to see how the resulting radii compares to the observed radii of the TRAPPIST planets. So the disk evolution model that we adopted was from Hartman et al., and it was based on observations of T-Tauri stars. And so the gas surface density evolution is shown by these first two equations. We assume the disk is isothermal, but we adopt the temperature profile from the minimum mass solar nebula. And the surface density profile of the pebbles tracks the gas surface density, and we assume a pebble to gas ratio of 1%. Okay, so because the solid bodies are embedded in a gas disk, they're going to undergo type 1 migration, eccentricity, and inclination dampening. So these expressions for the accelerations the bodies experience from all of those effects were first put forward by Creswell and Nelson in this particular form for the purpose of being implemented into n-body code. And so what determines these rates is the timescales on which all of these mechanisms operate. And these timescales are taken from Tanaka et al. 2002. So T sub n is the type 1 migration timescale. T sub e is the timescale that eccentricity dampening takes place on, and same for T sub I is inclination dampening timescale. All of those timescales are scaled by T wave, which is the dampening timescale, which is a function of the disk properties. And so then these are all of the timescale expressions. So at each time step in the n-body code, we are calculating what are these accelerations for each of these bodies, and their orbits get modified accordingly. All right. In the Rebound X module, they are also accreting pebbles. And so we implement these expressions to simulate mass growth from pebble accretion. So pebble accretion is thought to take place in these two regimes, the Bondi regime and the Hill regime. Smaller bodies will first start accreting in the Bondi regime. This is in a 3D perspective, so they can accrete pebbles from the vertical profile as well. And this accretion will continue to take place until this transition radius is met. And the transition radius is this first expression at the top I've shown here. Once this transition radius is reached, the pebble accretion transitions from the 3D body branch into the 2D hill branch. And the body will continue to accrete pebbles in this way until it reaches the pebble isolation mass. The pebble isolation mass is the maximum mass a body can grow to via pebble accretion. Once it reaches this mass, it will induce a pressure bump just exterior to its orbit, which halts the influx of pebbles, thus suppressing pebble accretion for that body and all of the bodies interior to that body as well. So at each time step, we are calculating what is the radius of the planet to see which branch it's accreting pebbles in. We are updating the mass of the body based on how much pebbles it has accreted. And we are also calculating what is the pebble isolation mass for a body at that particular radius in the evolving gas disk. Once that pebble isolation mass is met, that body can no longer grow its mass via pebble accretion. And so it stops pebble accretion not only for that body, but also all the bodies interior to that body as well. So these are all effects that went into the new Rebound X module that we developed for this study. These are all of the parameters we adopted that these go into our disk model mainly, and also the starting distribution of the planetesimals that we initialized just exterior to the ice line in our simulations. And so all of these parameters were taken to reflect what we would expect for a disk around a TRAPPIST-1-like star. Okay, so we also implemented the effects of fragmentation into this study. This was part of my PhD work as well, was developing a fragmentation model for the embodied code Rebound. Prior to this, Rebound only modeled perfect mergers or perfectly elastic collisions. So I took scaling relations from these 3 studies, which were developed by looking at SPH simulations of collisions, resolving them, and then they created these scaling relations. I implemented this into a module for rebounds such that when a collision happens, you calculate these 2 parameters first. This is the impact velocity and the impact parameter. And then once you have those 2 parameters calculated, you can refer to their scaling relations to see how a collision should be resolved. And so the various collision outcomes that the model permits for are listed in this table here. And I'm showing a schematic of the collision outcomes just to the right. And you can also see the impact parameter and impact velocity parameter space for each of these collision outcomes. And so we found that modeling fragmentation in the pebble accretion paradigm is actually very important because when 2 bodies collide, if they produce fragments, those fragments in turn can grow their mass through pebble accretion. And we found that in almost all of the simulations, those fragments seeded at least 1 planet. So this became a key mechanism in producing the high multiplicity systems that we were intent on simulating.
Sorry, what's the difference between hit and run and uh, partial erosion?
Hit and run and partial erosion. So I think they actually get resolved in the same way, but they are just classified in 2 different ways for qualitative reasonings. I think in a hit and run, in that particular case, we don't model this, but if you wanted to, and I think future studies have done this too using this code, a hit and run is more likely to result in just mantle stripping, opposed to if you had a partial erosion with a lower impact angle, it might take off, a more like deeper chunk of the planet, if that makes sense. That makes sense, Sergey?
Um, I'm still So does it mean hit and run? It doesn't change the mass of the bigger thing, and the partial erosion, the bigger thing loses. Is that correct? I guess.
No, they do get resolved in the same way.
Okay, not elastic.
But in the hit and run, it's going to be a more oblique impact. And so qualitatively, it's going to be a more mantle stripping collision, which is not something that we track in these simulations. But if you wanted to do something post-processing where you were interested in the amount of, mantle stripping collisions, you could do that with this information. So it's
Okay.
basically just giving you additional information about a collision outcome.
Okay.
Okay, so for the bulk composition tracking, we initialized the compositions of the bodies using results from a disk condensation code. These results were taken from Lee et al. Study, which used a modified version of the Grains code from CAS in 1996, if you're familiar with it. How disk condensation codes work is it tracks how very young and hot protoplanetary disks cool in time and how different species condense out of the protoplanetary disk as it cools. And so the evolution for the disk and the temperature profile for the disk evolution for this particular study, those expressions are shown here on the left, and the final composition profile for the disk that we adopted for our studies is shown on the right. So we tracked 12 elements, and we use these profiles to initialize the compositions of the planetesimals and to initialize the compositions of the pebbles in the disk. So after we initialize the compositions of all the bodies, we use this bulk composition tracking algorithm. So in a collision, a target is the bigger of the two bodies involved, and the projectile will be the smaller of the two bodies involved. Big X here, this is the composition of the target, where X sub I is the relative abundance of the ith species. So if you sum up all those relative abundances, they should equal 1. And similarly for the projectile, the composition is shown in big Y. So if you have a collision outcome where the target accretes some of a projectile of a differing bulk composition, it gets resolved accordingly to the X prime expression. And so this expression changes slightly based on what the actual collision outcome is, but that's the general process. And we do the same thing for the pebbles as well. Y sub peb represents the composition of the pebbles in the disk. Y peb sub I is the relative abundance of the ith species that you're tracking for the pebbles. And so at each time step for each body, we calculate what is the amount of pebbles that have been accreted over this last time step and over what radial range were the pebbles accreted so that we can adjust the bulk composition accordingly to that X prime position, that X prime expression shown there. So this is something we do post-processing after we formed our final systems. So this is going to be a video of one of our runs. The orange dots here are the actual observed TRAPPIST planets. I put them there for reference. The blue vertical line is the location of the ice line. These black diagonal lines are the pebble isolation mass. And then down at the very bottom of this plot, you can see some, or you might not be able to see, but there are small blue dots. Those are our starting planetesimals. And so we have planet mass on the vertical axis and semi-major axis on the horizontal axis. So when I press play, you'll see that these bodies very rapidly grow their mass. And they're growing their mass both through pebble accretion and through merging with one another. And they can continue to grow their mass through pebble accretion until they reach this pebble isolation mass, where again, it will halt pebble accretion, not just for that body, but for all the bodies interior to that body as well. And then you will also notice the bodies migrating inwards through type 1 migration. So you can see already planets getting trapped in mean motion resonances. And they will stay there until they experience this external gravitational forcing from these inward migrating planets, which breaks those mean motion resonances and causes these planets to merge in the inner regions of the disk. So this is what one of our final runs look like. And we integrate all of our runs for 3 million years. And so I think we did a pretty good job at creating TRAPPIST-like systems. One of the most important features to recover is, of course, the high multiplicity of the system, which we did. Another feature that we were able to recover was the relatively large planet masses of the two innermost planets. And as you saw in the video, this happens as a result of those resonances being broken and the inner planets merging to form these larger planets in the system. We also recover that you get a smaller planet kind of nestled in the middle of the system. And this happened because bodies exterior to that planet reached the pebble isolation mass before it did. So, more statistically speaking, though, we did 100 runs. And of these 100 runs, we formed 24 TRAPPIST analogs. And we call a run a TRAPPIST analog if it formed at least 6 planets. And again, as I mentioned, we found that fragmentation was very important in producing these high multiplicity systems, since a fragment contributed to the growth of at least 1 planet in all of these TRAPPIST-1 analogs. So if it didn't form a TRAPPIST-1 analog, then what happened was it formed fewer planets that were more massive. And so these planets were in the super Earth or even sub-Neptune range. Okay, so to get the bulk composition, we applied that post-processing bulk composition tracking code I showed before using compositions that were initialized from disk condensation simulations. We then looked at all of our TRAPPIST-1 analog planets. We bin them into radial bins that correspond with the observed TRAPPIST planets. And we took the average of the compositions for on each radial bin. And that's what I'm showing in this plot here on the left. I show what the relative abundance is for each of those simulated TRAPPIST analog planets for water and 12 elements. And I also show Earth's composition as well for reference. So we take these bulk composition results and we feed them to Magrathea, which is an interior structure code created by a postdoc and some graduate students at UNLV. And what we did was we assumed that all of the iron goes into the core and everything else goes into the mantle. And we assume that all the water resides on the surface as a hydrosphere. And then Magrathea calculates what the resulting planet radii are. And so I've listed R sub P, those are simulated planet radii, and RO are the observed planet radii. And we find that we did a pretty good job at producing the observed planet radii. The biggest discrepancies, though, in the planet radii were for planets B and C, where we were simulating planets that were larger than have been observed. So we took another approach where instead of assuming that our bodies start with a 20% water mass fraction, which is what we did, and this is something we chose experimentally because the grains code does not calculate ice condensates. So you have to make assumptions of what your initial water mass fraction is. And so we experimented with different water mass fractions until we got results that look good. And we found that starting with an initial water mass fraction in the planetesimals of 20% worked best. But now, instead of doing that, if we instead just use our iron and silicon ratios, and then we fit for the resulting water mass fraction to fit the observed planet radii, we end up with these water mass fractions listed in this table on the left. And what you'll notice about this table is that we do not have water mass fractions for planets B and C. And this is because using our iron and silicon ratios, we could not find solutions to a 3-layer model that matched the observed planet radii. So instead, we took a different approach and we assumed that instead of having a 3-layer model, the planets were desiccated. And so they only have a core and a mantle and no water. And so we vary the core mass fraction, and we do 5,000 draws with varied core mass fractions to see if we can recover the observed planet radii in just a 2-layer model. And so we were able to do that in excess of 90% for all of the planets, except for the outermost planet, H. And this is expected. You would expect the outermost planet to have the most water content. Where it resides currently is at the system's current ice line. And so we expect that planet H actually does have a significant hydrosphere. But 2-layer models are consistent with the rest of the planets. And a two-layer model is actually favored for planets B and C, using both our bulk composition constraints and when we consider the evolution history of those planets. If you recall from the video, the inner two planets underwent a series of late-stage giant impacts, which could likely remove any surface oceans those planets would primordially have. And so we were excited to see that while this paper was under review and we were explicitly predicting that the inner two planets, B and C, were desiccated, Tom Green's observations from JWST of TRAPPIST-1b and C came out, and they did not detect an atmosphere on that planet. And to lower confidence, but with similar results, they were also not finding an atmosphere on planet C. So we were very excited to see that our predictions were consistent with the most recent James Webb observations. Okay, so then the next thing we were interested in asking was, where are the other TRAPPIST-1 systems? Why are we only finding one system like TRAPPIST-1? There are other high multiplicity compact systems, but TRAPPIST-1 is an anomaly in the sense that it's around such a small star. And if we think that systems around small M-dwarfs are forming in the same way, then one might expect to find other compact high multiplicity systems around such low mass stars. But that's not the case. We're not finding the same compactness and multiplicities around M-dwarfs. So to answer this question, we looked at the our previous simulations, which were first initially integrated for just 3 million years. We turned off all gas effects. So no more inwards migration, no more eccentricity or inclination dampening from gas drag. These bodies are now free to interact through purely gravitational forces. And we extend those simulations up to 100 million years. We then look at the final system architectures at 100 million years compared to what they were at 3 million years. And based on that evolution over that time, we break the runs into three groups. We have our primordial low multiplicity groups. So these are the runs that initially formed fewer than 6 planets at 3 million years, and we're able to retain all of those original planets at the 100 million year mark. We have our unstable runs, where the system loses at least one run, most commonly in the form of a planet merger, although we had a couple runs where we lost planets from an ejection as well, but it was by and large through a planet merger. And then also our TRAPPIST-1 analogs, where the system formed with at least 6 planets at 3 million years, and it was able to retain all of those original planets at 100 million years. So after we partition our simulations into each of those three groups, we look at the distributions of 4 dynamical metrics that are commonly used when we talk about the stability of planetary systems. We look at the period ratio distributions. We look at the planet pair mass ratios, the system angular momentum deficit, which is basically a measure of how excited the orbits are in that system, and also the distribution of the delta metric, which is the orbital spacing of the planetary system. And so this is showing the distributions for those 3 subgroups in each of these 4 metrics that I just described. And we find that the unstable runs have a statistically different distribution from the TRAPPIST-1 analogs and the primordial low multiplicity runs. So these, again, are the runs that experience really no evolution in their system from when they formed in the gas disk to 100 million years after the gas disk has been turned off. We find statistical differences in 3 of the 4 metrics, those being the period ratio distributions, the angular momentum deficits, and the delta metric. In the top right-hand corner is the distributions of the mass ratios for adjacent planet pairs. And we do not find statistical differences between those 3 groups, but we do find that the unstable runs get shifted slightly to lower values, which is what you would expect if the planets are undergoing mergers, because they start to move away from uniform values. So where we find the biggest difference between these groups, though, is in the period ratio distributions, which are shown in the top left-hand corner. in the unstable runs, after a planet merger takes place, those period ratios get shifted to values larger than 2. Whereas the stable runs, those period ratios remain less than 2 for the most part. And so we see this as a the clearest sign that there was a dynamical instability in the form of a planet merger that took place in the simulation. And so then the next thing we do is we say, can we find the same signature in the observations? So to do this, we first query all the multi-planet systems around M-dwarfs. And we look at only systems that do not contain a planet larger than a super-Earth. And the reason why we impose this condition is because we want to do an apples to apples comparison between the observations and the simulations. And if you have a mass of planets in your system, it can influence the formation pathway in ways that we did not simulate. We don't have any giant giant planets or even smaller in our simulations. So we want to make sure that we're looking at observed systems that might have formed in a similar way. So once we have our final subset of the observed planetary systems, we break them into 2 populations. We look at the period ratios in each observed system. And if there is a period ratio greater than 2, that goes into what we call the big PR group. However, if all of the period ratios in a system are less than 2, that goes into the small PR group. So we end up with a final sample of 64 planets and 26 systems for the big PR group. And in the small PR group, we have 28 planets and 8 systems. We then calculate, so once we have our 2 populations in the observed sample, we calculate the same dynamical metrics that we did for our simulations. And we find really, really good agreements. We find the same statistical differences in those 3 metrics, which were the period ratios, the angular momentum deficit, and the delta metric. So we find the same trends and the same degree of statistical difference between those 2 populations. And then just like the simulations, though, we didn't notice there's not a big difference between the adjacent planet pair mass ratios. And so we take this then to be very strong evidence that we can identify specific systems that experienced a late stage dynamical instability in the form of a planet merger without the stabilizing effects of gas. And so you might be asking then, well, why is this important? Why do we care about which systems underwent a late stage giant impact? Well, because it can have important implications for habitability. When we talk about the search for habitable worlds and the search for life, it's very strongly guided by what we know about Earth. And so following this line of thought, we should then also be prioritizing systems that have a dynamical history similar to what Earth experienced. And it's Earth's violent history that is responsible for a lot of its habitable characteristics, such as the presence of a moon, our molten core, which in turn gives us our magnetic field and protects us from the sun. It could be responsible for plate tectonics, a secondary atmosphere, and really a lot of other habitable characteristics. And so if we can identify specific M-dwarf systems that might have experienced a similar dynamical history, then we should be prioritizing these systems in the search for habitable worlds. And so to summarize, TRAPPIST-1 planets likely formed through pebble accretion, and our results, where we also track the bulk composition of these planets, suggest that the inner 2 planets are desiccated, which have been confirmed by James Webb. We've also shown that dynamical instabilities leave relics in the observables of these systems, specifically that the presence of a period ratio greater than 2 strongly suggests that that system experienced a late stage dynamical instability, which might make it more preferable for habitability. And so that allows us to identify 26 specific M-dwarf systems that might have more habitable planets than the systems that form primarily through pebble accretion and did not experience the same degree of dynamical modification. And that's it. That's all I got. Thank you.
Excellent. Thank you, Anna. Do you have questions? If you have questions, just ask.
Okay. Yeah, can you great talk by the way. Can you go to the video you showed earlier that was like the evolving with the ice line? So kind of like more of a numerics question, like or what you're doing in the code. So you have this ice line. When the particles pass through the ice line, do you just kind of instantaneously change the composition to represent like sublimation across that ice line, or how do you handle the or is there any composition differentiation with ice line? Or I guess, yeah, what does the ice line serve other than this the pebble isolation mass?
Yeah,
Is
so
that
it's mainly the pebble isolation mass.
okay?
Yeah, the composition of the disk is fixed, and so is
Okay.
the initial composition of the planetesimals.
Is there any plans to dynamically track the composition, or do you think that would change any of the results or anything? Or
No, that sounds like it'd be really expensive to kind of do a
yeah,
real-time composition
right.
change.
Okay. Thank you.
May I ask about the same plot? Why is the pebble isolation mass discontinuous at the ice line? That should depend only on the on I mean on the ability of the planet to carve a gap, right? It's just the mass.
It depends on the Stokes number as well. So
Yeah,
it's largely
okay. I was
we
wondering
take,
about yep.
yeah, it's two different Stokes numbers.
And where is the Stokes number going on here? Oh, okay, on that square root there. But
Yeah,
but what is the physics of that specifically? Is it the gap being leaky for some Stokes number, but not to other Stokes numbers?
I'm not sure. I don't know. Maybe Chao Chin knows.
Don't know either.
Yeah, I
Like
mean,
a filter, it acts as a filter then?
yeah, like the gap is gonna trap larger pebbles. I mean, the gap side, right? It will trap larger pebbles, but it's gonna let the smaller one filter. So, if the
Yeah, well, also
mhm,
we just assume two Stokes numbers, one on the inside, interior to the ice line, and a different one exterior to the ice line. But I'm sure in reality, it's not such a stark discontinuity. So I don't know if it would be a real gap there. But it doesn't actually, the only thing it really changes in our simulations is the pebble isolation mass.
mhm. And it's the smaller pebbles inside the ice line, right?
Yes.
Okay, so I have larger pebbles out and in, and
Hmm.
small pebbles in. Okay, yeah, well, yeah, larger pebble isolation mass means that they continue growing, right? So you need more mass to halt the pebbles, which is consistent with a more leaky gap for smaller grains. Okay, right. I have another question. You mentioned in the beginning, trying to find it, that contrary to the solar system planets, right? That the planets of TRAPPIST-1 are thought to be formed by pebble accretion, contrary to what is thought for the solar system inner planets. I mean, why do you say that? Are you assuming that the solar system inner planets are formed by planetesimal accretion?
Yeah, I think that's the standard formation channel for solar system planets is core accretion paradigm, mainly because of the larger dynamical spacing of the um, rocky planets in the solar system. And that was something actually that the one of the refs, Dan Tamayo was actually the referee on that last paper. But as we showed that when a system undergoes a dynamical instability, it moves the planets to wider orbital spacing, which is what we see in the solar system. And so at that point, then it's hard to distinguish between systems that form through pebble accretion and then later went unstable and systems that form primarily through core accretion. So I guess then with that same line of thought, actually I'm remembering now too. I think another argument against the solar system planets forming through pebble accretion is that we have giant planets, exterior. We have external giant planets in the solar system, which could suppress pebble accretion for an inner rocky system.
If I could follow up on that, I guess one question, and maybe you said this, but what is this must be sensitive then to the assumed amount of mass in pebbles versus those that form into planetesimals, which is a major unknown, right? It
Yeah.
depends on your planetesimal formation mechanism, and So do you have any comments on that?
So that was also something we had to determine experimentally. There were a
Mhm.
lot of free parameters in the study that had to be fine-tuned to produce the TRAPPIST-1 analogs. And so starting with like the initial mass of the planetesimal population and the spatial distribution of the planetesimals were something that we had to experiment with to produce our best run scenario. So, I mean, I spent months playing around with different initial conditions to get, results that look like the TRAPPIST-1 system.
Yeah, so one general thought of these sorts of studies is that you get such a variety of outcomes, and so it's almost like fine-tuning is necessary and not necessarily a bad thing, right? Because if you can back out the parameters necessary to form a specific system. I guess one concern I always had is that, well, that's a strong thing. That's a good thing to do, right? Can you use that then to make any sort of predictions for what you should see in other systems? I guess you've already sort of talked about that a little bit, but did you have anything else any other comments on that?
Well, I mean, I'm kind of new to all the stages of planet formation that take place before this. But yeah, perhaps it could be used to inform some earlier initial conditions.
Yeah.
Within body dynamics is not deterministic anymore.
Yeah.
Right, but you could do maybe some sort of statistical thing, right? Like
That's what
population
NI
studies.
was doing using 100 systems.
Right, right. Yeah, I guess I was just thinking like if you have a certain set of parameters that leads to TRAPPIST, so I don't know, maybe I missed this. Did you actually predict like how many systems should be like TRAPPIST out of the whole?
No, so that's actually something that, has garnered some interest in this work too,
Mhm.
was what was the occurrence rate of TRAPPIST-like systems that you
Yeah,
were
yeah.
able to produce? And like long term, we were only able to maintain 8 runs that retain that initial high multiplicity of 6 or more planets. And so that was interesting in the fact that even though we cherry picked these initial conditions to produce TRAPPIST-like systems, it was still very difficult to maintain them long term without gas effects.
Yeah.
So we don't
Okay.
know what exactly the occurrence rate of these systems should be. Based
Mhm.
on our work, it kind of seems like it should be low because you do need a very specific resonance configuration for them to remain long-term stable. But I mean, perhaps if we did have an occurrence rate, we could do something like what you're suggesting. Figure out what is the initial distribution of planetesimals that produces the occurrence rate, and what does that teach us about planetesimal formation?
Mhm. Yeah, it might be, I would worry it might be degenerate with all the other parameters, but or not all the other parameters, but some. But anyway,
Yeah, there's a lot.
I've taken a lot of time. Very good talk, but I'll let others ask questions now.
Do you have more questions? So I'll ask another one then. Yeah, so I would add that the inner solar system planets, we are still debating if they formed mostly by pebble accretion or planetesimal accretion. Indeed, one of the things that you said, right, that the presence of giant planets could block the pebbles. It ties back here to this plot, right? That the small grains can actually go through, and then you could recoagulate them in the inner disk and replenish the pebbles. So it's excellent that you are showing how these planets can grow primarily by pebble accretion. So my question is, have you tried a hybrid model, like both pebbles and planetesimals, and see which one is the dominant source of growth?
Well, well, I mean, we're doing that to an extent here because we allow the planetesimals to interact with each other and accrete one another. Uh, um, but I think, at least for the parameters that we chose, pebble accretion is the dominant mechanism for mass growth. Um, yeah, and I think that's kind of the question, right? Because in reality, both processes are likely at play, and it's about determining was the dominant mechanism and, to what extent does each mechanism operate.
Okay, right. Good. So if you don't, yes,
I have one. Sorry. Could you explain again? You made a statement, and I think I just spaced out or something, but you made a statement as to why the inner planets are larger, like the inner two planets become larger. And I forgot exactly what you said. I thought what I heard was interesting, but I can't remember exactly what you said.
So in the video, you see that the planets, they kind of form in the same way until they stall up in these resonance locations. But as the outermost planets continuously move inwards, it forces the inner planets inwards more until the resonances break and those planets merge together, which is how they grow their mass.
So the outer planets are breaking the resonances, but basically, okay, interesting. All right, that's all questions I have, I promise.
Oh, I guess on this note then, when the outer planets come in and it forces the innermost planets to merge, what's the, I guess, occurrence rate between like an ejection or like a merger, like I guess among all the different ones you had?
Yeah, I mean, I think I don't remember the exact numbers, um, but I think that we only had like a handful of planet ejections.
Oh, really?
Yeah,
Oh,
it was very small. And even in those runs where you do have a planet ejection, it's usually accompanied by a planet merger. So by and large, the instability outcome is a planet merger.
interesting.
Okay, and with that, let's thank Anna again.
Thank you, Anna.
Thank you.
And I'll stop the recording now.